Multilayer perceptrons training a perceptron. The perceptron defines a hyperplane, and the neural network perceptron is just a way of implementing the hyperplane. Given a data sample, the weight values can be calculated offline, and then when they are plugged in, the perceptron can be used to calculate the output values. In training neural networks, we generally use online learning where we are not given the whole sample, but we are given instances one by one and would like the network to update its parameters after each instance, adapting itself slowly in time. Such an approach is interesting for a number of reasons. One, it saves us the cost of storing the training sample in an external memory and storing the intermediate results during optimization. An approach like support vector machines in Chapter 13 may be quite costly with large samples, and in some applications we may prefer a simpler approach where we do not need to store the whole sample and solve a complex optimization problem on it. 2. The problem may be changing in time, which means that the sample distribution is not fixed, and a training set cannot be chosen a priori. For example, we may be implementing a speech recognition system that adapts itself to its user. The reason 3 is that there may be physical changes in the system. For example, in a robotic system, the components of the system may wear out or sensors may degrade. In online learning, we do not write the error function over the whole sample but on individual instances, starting from random initial weights. At each iteration, we adjust the parameters a little bit to minimize the error without forgetting what we have previously learned. If this error function is differentiable, we can use a gradient descent. For example, in a regression, the error on the single instance pair with index t, x to the t, and r to the t is that expectations to the t of w conditioning on x to the t and r to the t is equals to 1/2 times the square of r to the t minus y to the t, which is equals to 1/2 times the square of r to the t minus, by definition, w transpose times x to the t. And for j starting from 0, 1, 2, 3 until d, the online update is delta wj to the t equals to eta times r to the t minus y to the t times xj to the t, where eta is the learning factor, which is a gradient decreased in time for convergence. This is known as stochastic gradient descent. Similarly, update rules can be derived for classification problems using logistic discrimination where updates are done after each pattern instead of summing them and doing the update after a complete pass over the training set. With two classes for the single instance, x to the t, r to the t, where I to the t is equals to 1 if x to the t is in C1, and ri to the t is equals to 0 if x to the t is in C2. The single output is y to the t equals to sigmoid of w transpose times x to the t, and the cross entropy is as follows. Expectation to the t of w conditioning on x to the t, r to the t is equals to minus r to the t of times log of y to the t minus 1 minus r to the t times log of 1 minus y to the t. And using gradient descent, we get the following online update rule for j equals to 0, 1, 2, 3 until d. That is delta wj to the t equals to eta times r to the t minus y to the t times xj to the t when there are k greater than 2 classes. For the single instance, x to the t, r to the t, where I to the t is equals to 1 if x to the t is in Ci and 0 otherwise, the output are yi to the t equals to exponential of wi to the t times x to the t. divided by sigma k, sigma for all k of the term exponential of wi to the t times x to the wk to the t times x to the t, and something for all k. And the cross entropy is expectation to the t of the set of wi for all index I, conditioning on x to the t and r to the t, is equals to minus times sigma summing for all I of the term ri to the t times log yi to the t, and using gradient descent we get the following online update rule for I equals to 1 to 3 until k, and the j equals to 0, 1 to 3 until d, and the delta wij to the t is equals to eta times ri to the t minus y to the t times xj to the t, which is the same as the equations we saw in section 10.7, except that we do not sum over all of the instances but update after a single instance. The pseudocode of the algorithm is given in figure 11.3, which is the online version of figure 10.8. Both equations 11.7 and 11.9 have the form update equals to learning factor times desired output minus actual output, then times input. Let us try to get some insight into what this does. First, if the actual output is equal to the desired output, no update is done. When it is done, the magnitude of the update increases as the difference between the desired output and the actual output increases. We also see that if the actual output is less than the desired output, update is positive if the input is positive and negative if the input is negative. This has the effect of increasing the actual output and decreasing the difference. If the actual output is greater than the desired output, update is negative. If the input is positive, and positive if the input is negative. This decreases the actual output and makes it closer to the desired output. Okay, let's see. Figure 11.3 is a Perceptron training algorithm, implementing stochastic online gradient descent for the case with k greater than 2 classes. This is the online version of the algorithm given in figure 10.8. Okay, first there are two levels of for loop. For I starting from 1 to k, for j starting from 0 to d, we assign wij equals to some random variable, which the rand is chosen among minus 0.01 and 0.01. Note that this is the open interval from both sides. And instead of that, we do the repeat. Repeat with the following two layers of for loop. For all x to the t, r to the t, and x in random order, we do the following three sequential of for loop instead of this big for loop for all x to the t and r to the t and x. The first for loop is for I starting from 1 to k. We assign oi equals to 0, and instead of that, we do an inner for loop for j starting from 0 to d. We assign oi equals to oi plus wij times xj to the t. We have been familiar with that when we discussed the formulas before. Okay, then if we break out from those two layers of for loop, the next sequential for loop is for I starting from 1 to k, we assign yi equals to the exponent of oi divided by the sigma of exponent of ok, summing for ok. And the third level of the for loop is for I starting from 1 to k. Instead of that, for j starting from 0 to d, we assign wij equals to wij plus eta times ri to the t minus yi, then times xj to the t. Now this will repeat of the third levels of for loops will repeat until convergence. When an update is done, its magnitude depends also on the input. If the input is close to 0, its effect on the actual output is small, and therefore its weight is also updated by a small amount. The greater an input, the greater the update of its weight. Finally, the magnitude of the update depends on the learning factor, eta. If it is too large, updates depend too much on recent instances. It is as if the system has a very short memory. If this factor is small, many updates may be needed for convergence. In section 11.8.1, we discuss methods to speed up convergence. So this is about the training a perceptron.